Now, in this video, we're going to walk through some examples of doing Lagrange multipliers for optimization problems. Now, one precursor that I want to mention is that I originally designed these examples to for my business calculus students so that they could also solve these problems. And so we don't use the gradient notation in this discussion. The method that we're going to use for this is algebraically equivalent to that gradient approach that you will see in traditional calculus textbooks, or at least in some traditional engineering type calculus textbooks. But we avoid using the gradient notation here because the business calculus students don't learn it, and so it would be completely alien to them. So I wanted this to be examples that I could use both for my multivariable calculus students and also my business calculus students. So let us continue. Now, Lagrange multipliers, again, they are a way of doing optimization problems where we have a function that is subject to at least one or more additional constraints. Now, when we do one variable problems, we have encountered problems like this before, where we have some sort of like we're optimizing a fence, but we have a limitation on how much area we can contain, or vice versa. We want to optimize the area, but we have a limited amount of fencing or something to that effect. So these are going to be similar kinds of questions, but substituting in our constraints into the objective function can sometimes make the algebra sort of blow up on us. And so rather than proceed in sort of the traditional way that we did in the one variable case, taking essentially a two variable problem, turning it into a one variable problem, and then proceeding from there, in these cases, we're going to end up potentially with two or more variables anyway. And so we're going to need some of these higher level algebra. We may not have enough constraints in order to get the problem all the way down to a one variable case anyway. And so this is another approach that we can use that can handle some of these more complicated scenarios. So we are going to have two functions at a minimum that we are going to be dealing with. We're going to have the function that we want to optimize in some fashion, and then we're going to have a constraint function, which I'll refer to as G. And in all of our examples, these are going to be functions of two or more variables. We're also going to see that at least potentially you can also have problems with more than one constraint. But we'll come back to that a little bit later. Let's first introduce just the basic idea with a nice simple example. So here we want to minimize the function x squared plus y squared, and we're going to subject it to the constraint 2x plus 2y equals 5. In this example, we're going to assume that both x and y must both be greater than 0. This is a common problem, particularly, again, in the business context where negative counts of things don't make any sense. This is not a universal requirement, but it is often applied in, again, in certain contexts when we do this sort of optimization. Now, the first thing that we're going to need to do is we're going to need to construct our function g as a function of two variables. Essentially, we're going to put everything on one side of the equation, set it equal to 0, and then that will become our g function. So here, we're going to move the 5 over, and then that is going to be our g. Now, the next thing that we're going to do is we're going to create the function we're going to optimize, which I'll call capital F. And we create this function, again, without the gradient analysis. This is our alternative. We're going to create the function big F by taking our constraint, our function that we're trying to optimize, and subtract lambda times our constraint function, so minus lambda g. And so this will give us a function of now three variables, x, y, and lambda, x squared plus y squared minus lambda x minus 2 lambda y plus 5 lambda. And so what we then want to do, because it's an optimization problem, is we want to take the first derivative of all of these functions of our f function with respect to all three of our variables. So if we take the derivative with respect to x, we get 2x minus lambda. 2x comes from here. Lambda comes from here. The derivative with respect to y, the partial derivative, we get 2y, which comes from here, and 2 lambda, negative 2 lambda, which comes from here. And then f lambda is basically just going to give us our negative g. And we set all of these equal to 0. We get 2x is equal to lambda. Lambda is equal to y. And this was our original constraint. Now, you may notice, essentially, that these two components are the gradient for f, and this is essentially just taking the derivative of the original function. It's lambda times g. Well, if there's no, the lambda derivative got canceled out. So it's the derivative with respect to lambda of the lambda g function. And as I noted, the gradient approach is algebraically identical once you make all of the pieces equal to each other. You will get these same relationships if you do this example by the gradient method. So we'll notice that the lambda derivative is just the original constraint. And we have this relationship now for lambda that can get us our relationship between x and y, a new relationship between x and y. So what I can do is I can create the second equation, 2x is equal to y, or I can substitute both of these into my constraint equation and solve for lambda. Now, in the end, the truth is we don't actually need lambda. If there's a way to solve this problem without solving for lambda, you can do that because we don't actually need the value for lambda. It is just a way of getting a relationship between the x and the y. But in this case, I solved for lambda by substituting these into my constraint equation and then solving for lambda, and then I can replace my value for lambda into these two equations. So I end up with x is 1 and y is 2. You will get exactly the same result if you substitute just 2x equals to y, getting rid of the lambda at that point, and then substituting that into your constraint equation to solve for either x or y, and then from there, solving for the remaining variable. So you do not need to solve for lambda. That is one way to get to a solution for x and y, but you do not actually need to solve for lambda. But what we conclude, regardless of how we get there, is that our critical point here is at 1, 2. And so the maximum, the optimal value for our equation subject to this constraint is 5. Now, this was a minimum. The problem told us in advance that this was a minimum. We could do some additional analysis in order to try to verify that. But generally, for these kinds of problems, that's not really necessary. Now, this technique for solving this problem subject to this constraint, there are other ways to go about solving it. And so just, again, so that you're aware of the variety of ways that you can go about this, you can use this constraint to try to turn this into instead of a problem of 2 variables, a problem of just 1 variable. So here I've solved for x in terms of y. I can substitute my 5 minus 2y in for x, and I get this. And then now I have a 1 variable problem. My z is in terms of y alone. I can FOIL this out. I can take my first derivative, and you'll see that you do, in fact, can get exactly the same solution. You get y is equal to 2, and when you substitute y equals 2 in for this relationship that we found, you get x equals to 1. So, and we can also see that, in fact, it is a minimum. So this is the Lagrange multipliers are equivalent to other strategies that we've used. Sometimes the algebra on these things will kind of blow up. And so Lagrange multipliers turns out to be a little bit easier. There's a little bit, I wouldn't say less algebra, but it's algebra of a slightly different kind. And so this is an alternative, and you do get exactly the same solution. Now, let's try a slightly more difficult one, this case with 3 variables subject to this constraint. So again, we're going to create our g function by moving everything to one side of the equation and setting that equal to 0. That becomes our g. And then our big F function is our maximize or minimize problem minus lambda g, so f minus lambda g. And so we get this big nasty thing. Again, lambda, I distributed it through our g along with the minus sign. And when I take my derivatives, I now have to take 4 first partial derivatives. So f sub x, 2x minus lambda, f sub y, 2y minus lambda, f sub z, 2z minus lambda. We get all of those 2x, 2y, 2z's from here. And then the lambdas all come from here. And then the derivative for lambda, that's going to get us just the negative of our original constraint, basically. And when we set it equal to 0, it is in fact our original constraint. So for each of these fx, fy, and fz, I'm going to solve for, essentially for lambda. So here I'm going to get, oh, this should be a z. It's a typo. X is 1/2 lambda, y is 1/2 lambda, and z is 1/2 lambda. And again, I have some alternatives in terms of how I want to solve for this. In this example, what I did was I plugged in all of my x, y, and z values in terms of lambda into my constraint. And so I have 1/2 lambda and 1/2 lambda and 1/2 lambda, which is 3/2 lambda is equal to 1, which means lambda is 2/3. And then if I use that relationship in my equations in terms of x and lambda, then I end up with 1/3 for all of these values, because 2/3 times 1/2 is 1/3. And then let's look at one example where we are subject to 2 different constraints. How would you include those? Well, in this case, we're going to have 2 constraints. We'll call this one g, and then this one we'll create an h function for. And then we'll also have 2 of these Lagrange multiplier cases, not only lambda, but also mu. So we'll have a second dummy variable. So we move everything over to one side, we get our g function, we move all of these terms over to one side, set it equal to 0, we get our h function, and then our capital F function that we're now trying to optimize is that regular maximization or minimization problem minus lambda g minus mu h. And so here's our original F minus lambda g minus mu h. And then our function now, it has 3 initial variables plus lambda and mu. So we need to take 5 first partial derivatives. So the derivative, let's go back and look at our function. The derivative for x is going to be yz, and then minus lambda, and then also minus mu. Fy, xz minus lambda plus mu. Xy for the derivative for z minus lambda minus mu. Our derivative for lambda, again, it's just these terms right here without the lambda. And then our derivative for mu, again, it's these terms without the mu. It's just these 2 are our initial constraints. The negative of them in this case, but equal to. Now, we have a little bit of algebra that we have to do here to try to deal with these equations. We have more variables, and so things can become a little bit more complicated. So in this case, what I've done is I have two of my equations, one that has a plus mu and one that has a minus mu. So if I add them together, I can eliminate the mu. And then I take two of my other equations. In fact, the second one is the same, but I can take my other expression for z, from the derivative for z that has minus mu in it, and combined with this plus mu, I can add them together and eliminate the mu, and so I end up with this. And so when I solve this, I get yz plus xz is equal to 2 lambda. And this one, if I move the lambda, 2 lambda over, I get xy plus yz is equal, xz is equal to, xy plus xz is equal to 2 lambda also. And so I can substitute one of my expressions for 2 lambda into my other equation. So yz plus xz is equal to xy plus xz. I have xz on both sides of the equation, so they disappear. Yz is equal to xy. I cannot divide out the y. I have to put everything on one side of the equation and factor out the y, because y equals 0 is a solution, and I can't guarantee that it's not 0. So I factor it out. And so I end up with two possibilities. Y is equal to 0 or z is equal to x. And then likewise, I can simplify my constraints equations. I can put those together. I can add them together in order to get rid of the y's. And I'm left with this relationship between x and z, and they have to collectively be equal to 16. So again, in this example, I haven't found lambda or mu, but I have found additional relationships between x and y, and x and z. Now, if I use the y equals 0, I don't have any expressions in here that relate to y. So instead, I'm going to use this requirement here that z minus x equal to 0, which means that x has to be z. So if x is z, I can substitute in here x and x. I get x and x is 16, so x is 8, which also means that z is 8. And then if both of those are 8, then I can plug that into one of my other constraints and discover that y has to be 16. And I can see that, in fact, this will also work in that second constraint. 16 and 16 minus 16 does, in fact, equal 0. So our final point is 8, 16, 8. Well, what about y equals 0? Well, if you are not told explicitly that these variables must be greater than 0, that is a possible solution, and you need to go ahead and get more than 1 point. So we could plug in y equals 0. That would imply in this constraint equation that x plus z is equal to 0, so x is equal to negative z. And that would cancel out these equations, these z's, in which case you would end up with y is equal to 32. But this is a contradiction because we started out by saying y was 0, and we plugged that into one of the constraints, and we got x was equal to negative z, and then we plugged that into the second constraint, and that's what led us to y is 32. So it is not possible to satisfy both of these constraints with the y equals 0 case, so we no longer have to worry about it. Our condition was an or. We do have to check it to see if it works, because in theory, you could have more than one optimal solution. But in this case, it turns out that y equals 0 solution does not actually produce viable optima.